Hello and welcome to my talk about our paper concerning the forensic ability of neural network inference pipelines. This paper is joint research with Tobias Kupek and Rainer Böhme. Let's talk about what our title even means. One would assume that machine learning inference is a deterministic process, which is true, at least to some extent. We verified that executing the same exact model on the same exact input multiple times on the same CPU gives you identical results. However, if we execute the model on different CPUs, we can get different results. Hello! Hey look, it's me, again. I know what you're thinking, that is the wrong video. And you're right. Today we're talking about the same thing, but instead of the principle itself, we're talking about how these different results affect the decision boundaries. So with some movie magic, let's start from the top, shall we? In the original paper, we showed that you can use softmax outputs to identify different CPU microarchitectures and presented the concept of boundary samples. In this follow-up paper, we show how to use boundary samples as telltale watermarks. Each boundary sample tests a binary hypothesis for one microarchitecture. This way, we can identify the true microarchitecture among a closed set of candidates using only the argmax labels. Before I tell you how we propose to create boundary samples, I would like to explain the term. In this graphic, we see two decision boundaries B0 and B1 arising from two different microarchitectures. A correctly classified benign sample lies in the white area and is shown here as a dot. For the purpose of adversarial samples, we want to move past the decision boundary in all microarchitectures into the dark blue area in the graphic. For our telltale watermarks, however, we need a sample that lies in the light orange area between the decision boundaries, hence the name boundary samples. Samples in this area result in different labels on different microarchitectures, allowing for identification. For realistic scenarios, the area where we can move the sample in feature space is limited by a distortion constraint. We use the peak signal-to-noise ratio, or PSNR, and require a minimum of 50 decibels, which is the typical PSNR of JPEGs compressed in good quality. PSNR is based on the mean square difference, and higher values mean less distortion. Given that boundary samples and adversarial samples are closely related concepts, we use the popular fast gradient sign method, or FGSM, as a starting point for our generation algorithm. While it is not the most sophisticated method, it is a good fit for PSNR constraints as it introduces many smaller perturbations instead of fewer large ones. To make the algorithm less sensitive to the step size alpha, we use the iterative form IFGSM. We make two additions to the classic FGSM step function. First, we need to approach the decision boundary, not move past it. We therefore require a scaling parameter that decreases the step size as we get closer to the decision boundary. For this, we use the confidence difference between the first and second predicted class and note it as delta conf. Second, we need to handle the case where the sample is misclassified, which means that we are already past the decision boundary. For this, we introduce a correctness indicator C. C is set to 1 if the sample is correctly classified and to -1 if it is misclassified. This ensures that every step takes us closer to the decision boundary. However, approaching the decision boundary alone is insufficient for the generation of boundary samples, as these must lay between the decision boundaries of different microarchitectures. Given two gradients, G0 and G1, each belonging to a respective decision boundary, we approach the closer decision boundary given by the smaller delta conf. If we approach but do not cross this decision boundary, we can just keep executing more and more iterations. If we move past both decision boundaries at once, we now target the other boundary and our correctness indicator takes care of the change direction. Once we hit the area between the decision boundaries, the two microarchitectures report differing labels and we have generated a boundary sample. Through smart choice of the target gradient, this approach can be extended to identify one microarchitecture out of n candidates. To single out a microarchitecture, we require the label on that architecture to be different from all others. We refer to the single different label as the identifying label and the others as contrast. In this figure, the highlighted area on the left indicates microarchitecture 0, which corresponds to decision boundary 0. When we move from class U to class V and we cross B0, architecture 0 reports a different label than all the other architectures and it can be identified. The same holds if we cross every boundary except for B3, which means that microarchitecture 3 is singled out. This area is highlighted on the right. As soon as two or more microarchitectures return the same label, the boundary sample is not identifying anymore, shown here in white. Note that the intersection between boundaries 1 and 2 is only meant to highlight the complicated nature of high-dimensional decision boundaries, and it carries no further meaning. The extended approach then works as follows. First, the current sample is predicted on all microarchitectures, including the calculation of gradients for each pixel. We then partition the results based on their predicted labels. From the smallest partition, we pick the second furthest decision boundary, which is the one with the second highest confidence difference. Passing that decision boundary leaves us in an identifying area, as only one microarchitecture has yet to flip its label. The full algorithm we used is shown here, and it also contains two special considerations for our experiment setup. First, we had 2 cloud instances per microarchitecture. Our exit condition then needs to take this into account, which is highlighted in line 10. The second special case occurs when every microarchitecture returns the same label. If this happens, we approach the closest instead of the second furthest boundary to reduce the number of steps that are required. You can also see here that we split the algorithm in a local phase and a remote phase. The local phase approaches the decision boundary, while the remote phase aims for the area between the decision boundaries. As we use cloud instances for a diverse set of microarchitectures, doing the bulk of the work on our local machines is both faster and cheaper. Recall that our boundary samples are binary classifiers, each answering the question whether a given microarchitecture was used or not. To identify one out of n candidate architectures, we then need a set of boundary samples, with one for each microarchitecture. We call such a set of boundary samples fully identifying. As our algorithm is untargeted, building a fully identifying set requires the generation of boundary samples in the hopes of identifying every microarchitecture. This sounds suboptimal, but we will see in a second that this is really not a big issue. To evaluate the efficacy of our boundary sample generation, we require different CPUs. For simplicity and reproducibility, we used instances on the Google Compute Cloud. We start every generation with benign samples from the FashionMNIST or FMNIST and Cypher10 datasets. The models used were both variants of the ResNet architecture with 20 and 32 layers for FMNIST and Cypher respectively. To be clear, we also used ImageNet as a third and much larger dataset, but we did not have any successful results for it. For our evaluation, we attempted generation of the first 400 samples from the test set of both our datasets. We limited the generation algorithm to 2,000 steps for the local phase and 500 for the remote phase. Additionally, we ensured that all processes were deterministic within each microarchitecture. The success rate for our simpler dataset is an impressive 70%. And the successfully generated boundary samples are split evenly between all our microarchitectures. This is important as it indicates that even without targeting, our algorithm can generate a boundary sample for each architecture with reasonable effort. For Cypher, the success rate is much lower at 28%, probably due to the larger cell space. This is supported by the fact that we did not find any boundary samples for the much larger ImageNet dataset. The next metric is the transparency of successful samples. Both median and mean are above our constraint of 50 decibels for both datasets. It's also visible that PSNR is higher for the more complex Cypher dataset. This is true for every statistical characteristic we examined except for the maximum. Again, this is presumably due to a larger search space, which also leaves more room to embed perturbations. Next, let's examine the required number of steps to generate boundary samples for both our datasets. Both datasets show a similar number of local steps, indicating a similar effort to approach the decision boundary. The number of remote steps, however, is much larger for Cypher than it is for FMNIST. The trend line indicates a much steeper relation between local steps and remote steps for Cypher, but this may be influenced by the fact that we have a lot fewer successful samples for FMNIST and thus much fewer data points. Unsurprisingly, the longer the search takes, the lower the quality of the resulting boundary sample. However, this effect is much more pronounced for FMNIST than it is for Cypher, where we observed basically no quality decay. Both the higher number of steps and the higher resulting quality for Cypher are presumably related to the larger input space. Overall, the difference between the two datasets indicates that much information can be gleaned from applying our generation algorithm to different datasets. To summarize, in this paper, we further study boundary samples, a special type of adversarial sample that can be used as watermarks to identify whether a given microarchitecture was used to perform the prediction. Contrasting to our initial paper on this topic, we do not need access to the softmax outputs and the final label is sufficient. Multiple of these boundary samples can be used to craft a fully identifying set, capable of identifying which of the n-candidate microarchitectures was used for prediction. Even though the presented algorithm cannot target a specific microarchitecture, a fully identifying set of boundary samples can be constructed with reasonable effort. Furthermore, even without enforcing a minimum PSNR of 50 decibels, these fully identifying sets can be constructed with all samples having a PSNR of above 80 decibels. The presented algorithm can be improved upon in multiple ways. Enabling targeting would drastically reduce generation effort, but probably requires the combination of multiple gradients. One way to achieve this would be using saliency map approaches like GSMA as a basis for the generation algorithm. This would also allow the enforcement of distortion constraints, which currently does not happen. Using pure black box attacks like zeroth order optimization could also lead to interesting results. An alternative direction is varying the input space. This work uses two small datasets for its experiments, and even there we observed significant differences. Scaling this analysis to more datasets could lead to interesting results, and based on our failure for ImageNet, this is a non-trivial problem. Similar, we assume inputs are provided as floats, which allows perturbations in a range of around 10 to the minus 7. Making boundary samples robust to quantization of 8 bit per channel seems like another promising avenue, but stands in direct conflict to a low distortion. All in all, the underlying phenomenon has potentially far-reaching implications on the security of inference results. Until authenticated inference results become a thing, a goal which I'm also working towards, boundary samples can be used to increase confidence in the source of a given prediction. Furthermore, boundary samples can be understood as adversarial samples targeting a specific microarchitecture. This paper thus tells a cautionary tale about the possible consequences of distributing inference over different hardware. Alright, to end this talk as it began, I will now play myself out. What I do not want to black box is the work on Enclave. If you like this presentation and are interested in the project, I would recommend reading the paper. For those who are more interested in the code, check out the repository for the framework and our experiments. If you have any suggestions, feedback, or even a contribution, don't hesitate to create an issue or a pull request. If you have any questions or would like to collaborate on a future project, please also feel free to get in touch with me via email or through my page on our research group's website. Thank you for listening.